Hello, and welcome to our presentation. We would like to thank you for your interest in our research in level control cooking systems. Deborah, Shai, and myself have been researching this topic for the last month and have a combined experience of 40 years of boiling water for cooking purposes. We know you have all experienced a pot of potatoes or pasta boiling over and creating a huge mess. With the controller we present to you today, we hope to prevent boilovers from occurring in the future. Without further ado, I'll begin the presentation. The objective of this project was to create a controller that manipulates the heat setting on an electric stove to boil potatoes efficiently without causing a boilover. To give you some background on the problem, when you add potatoes or starches to a boiling system, you introduce a starchy layer with a higher surface tension. This film makes it more difficult for the water vapor to escape the system, causing the layer to increase in height and potentially boil over. Current preventative technologies include pot washers, which accumulate smaller bubble vapors into larger ones that can break through the starch layer. Here's a picture of our experimental apparatus. We used 2 cups of potatoes and 2 cups of water in a pot and brought it to boiling on an electric stove. This right here is the heat control, or our manipulated variable. By turning this dial, we could affect how much heat input was put into this pot. The controlled variable is the pot level. We measured the pot using this ruler, and we measured it at 15-second intervals. Once the boiling reached steady state at a specific temperature, then we would change it. So we started off at 7.5. When it reached steady state, we went down to 5. And then when that reached steady state, we went to 6 on the dial. These are the results of our doublet test. The plot on the left shows our input steps with time, from 0 to 9. As regulated by the dial on the stove. The plot on the right shows the pot level as a result of the input changes with time. For the model to be adaptable to multiple pot sizes, we set the initial height of the water as our reference point and modeled the change in height. We decided to model only the portion of the step test after the initial dead time where the water is heating up. Our controller will just start whenever the water reaches boiling temperatures. We initially tried to fit the model to an FOPDT model, but while the second and third steps fit pretty well, we couldn't get that initial peak, which is really where the pot is most likely to boil over. And so we decided to do an underdamped second order plus dead time model. Using this equation right here, we fit our data, and we got our Kc, zeta, tau, and theta, and with that, we were able to fit our data and capture that initial peak, which is really the most important part. That's where it's going to boil over. When designing our controller, we needed to account for the very large dead time that was at the beginning, and also for the fact that the bubbles are constantly changing, so it's not a very set level. We decided to go with a proportional only controller. Now this is important because we wanted the offset that the proportional only controller can give us. Because we set the top of the pot as our set point, we didn't actually want the water to get to the set point. We just wanted to make sure that it never went over. We didn't want an integrating controller because of that really large dead time at the beginning. Also, we didn't want a derivative term in there because of the noise of the bubbles. That would just really throw off the controller. And so we decided to do a P-only controller. In order to get the Kc values that we wanted, it turns out that it's a nonlinear correlation between the set point and the Kc. So therefore, we came up with this equation right here, where the Kc actually depends on the set point, and depending on the height of the controller, the height of the pot is what the Kc will be. So at first, our model gave us a very, very smooth curve. And that's not very realistic because it's boiling water, so the level is just going to be constantly fluctuating. So in order to account for the noise that you naturally get in a boiling pot of water, we added a random noise. We added some variance into our model. This picture right here shows that we tried to copy the amount of noise that we saw when we did our doublet test into the model. And this right here shows that we did a pretty good job of matching up the level of noise in the controller and the level of noise in the data. Also to note, in order to take care of the variances, the equation for the Kc values actually goes below and takes into account the disturbances. With no limitation on the heat input to the system, our controller becomes unstable at a Kc of 3.77. That is shown from this root locus plot where it crosses the y-axis at approximately 3.77, which means that anything to the right is considered unstable and will cause instability in our controller. Our controller is actually inherently stable because it is limited by the amount of output that it can do. So our stove can do an output of 0 to 9, which means that it will never actually be able to go above 9. In conclusion, we have decided that a P-only controller is best for this model because of the large dead time and the noise in the data. We will also use a level sensor and a variable KC that will be changed based on the height of the pot. And our controller is limited to set points between 1 and 6 centimeters. So this means that if you're less than 1 centimeter from the top of the water, you're probably going to boil over. And if you're more than 6 centimeters above the top of the water, then you're not going to boil over and you don't actually need this controller.